Hi, this is Peter Rossi again to talk to you about uh, sample size calculations. A lot of people will ask you, how large a sample do I need to ensure a given level of precision in my calculations? Because after all, I'm using sample quantities like sample averages to estimate things like attribute importance or sales rates or consumption or willingness to pay, all these kind of variables, and that's why I'm undertaking my survey to inform some aspect of the success or potential success for my product. As I've mentioned in class, it's really far more important that you get a representative or high quality sample than so much that you have a large sample. That very large and non-representative samples can be actually inferior to smaller, more representative samples. But everyone does want to think a little bit about sample size calculations, and they do figure importantly in most sample survey contexts, so I do want to discuss them. Okay, so where does sample size calculations derive from? They come from sampling error. So the idea here is that what we're going to do is we're going to do a survey, and then on the basis of the survey, we're going to calculate something like y bar, the average of a variable. So for example, if we were to measure importance of a particular attribute on, say, a 1 to 5 scale, where 1 was very, very unimportant and 5 is very important, then we want to know something about the sampling error in our average. So we're going to measure the average of all those scales for each of our respondents. We're going to call it, that's y bar. And we want to know something about the amount of error in y bar. Y bar is an imperfect measure of the true population mean. If you recall that the amount of sampling error in y bar is determined by this formula for the standard deviation of y bar, the ratio of sigma to square root of n, where n is the sample size. What is sigma? Sigma is the variability of the population. So for example, if every single person in the population that I'm interested in sampling from had exactly the same views on that attribute importance, then we need a sample of only size 1. We need to measure that importance, but since everyone is identical, it doesn't bias anything to have a larger sample, because we now have a sample of size 1 measures perfectly the preference of that population. However, in any real marking application, that's not true. So whatever we measure is going to have some variability from respondent to respondent, or from one member of the population to the next, and that variability is captured by sigma, the standard deviation, okay, which is the square root of the variance. Okay. Typically, in our work, we express the degree of sampling error via a confidence interval. So the idea is here we present an interval of values. We say our best guess is y bar, but really plus or minus a certain amount is some notion of the margin of error. So most people understand that I'm measuring something imperfectly. My margin of error is plus or minus some quantity. For statistics, we can actually determine the margin of error based on a confidence level. So the idea of a confidence level is to say, let's specify a degree of confidence. For example, the most typical one, 95% confidence. Let's construct an interval that will contain the true mu, the true unknown population mean, 95% of the time, as an example. The general formula for confidence interval is this: y bar plus or minus a multiple of the standard deviation we discussed on the previous slide. So that z times the standard deviation is really the margin of error, okay, or which we're calling E. Okay, this z is a value from the standard normal random variable table, right? So that would determine the number of multiples. The one you probably remember is 1.96 or 2 approximately. That's associated with a 95% confidence interval. But in general, if I want to have more confidence, I'm going to have a larger interval. If I want to have less confidence, like a 90% confidence interval, I would use a smaller interval or smaller multiple of z. Okay. Now I can take this confidence interval formula here and invert it and ask the question, how large does n have to be to make this whole thing in this box here, the margin of error, no larger than a certain critical value? Okay, so for example, sample size calculations start with that by specifying the margin of error that can be allowed. So plus or minus how much are you going to be willing to allow? Specify the desired level of confidence. That's typically 95%. The desired level of confidence will determine the number of standard errors associated with the confidence interval. So for example, z equal 1.96 is associated with the 95% confidence interval. Z equal 2.6 or so, 2.57 is the 99%. So you can see if I'm using 99% confidence, I'm going to have a wider interval, as you'd expect. Okay, so and then solving that equation, n is equal to sigma squared z squared over e squared. E is my margin of error. Z is my multiple, it's either 1.96 or 2.57, so those are easy to determine. The only thing that's a little bit maybe difficult is sigma squared. What is sigma squared? It's the variance of the population. So you have to know something about the variance of the population you're trying to measure, or standard deviation. You can use a pilot sample to determine that. In other words, a smaller pre-sample that you do just for the purpose of determining this. If it's measured as a proportion or on a 5-point or multiple point scale, then you can actually estimate sigma squared in a worst case scenario. Okay, so let's go through those calculations. So first, let's imagine something I'm measuring a continuous quantity, like gallons of consumption of wine here. And then I first have to decide, in order to dictate my n, obviously as E gets smaller, n will get larger. So I've got to determine my margin of error. Here my margin of error is half a gallon. So again, what that means something relative to the average consumption rate. Okay, and then if I use a 95% confidence interval, that means z equals 1.96. That's easy. So my margin of error and my z value are something supplied by me. I pick my confidence level and I pick my level or margin of error. And then the only thing that's a little bit tough here is the standard deviation. So I have to know something about how variable consumption of wine is in gallons over individuals in the population. So here I've taken the example of a variance of around 4. Standard deviation of around 4. I put that in the formula and I get an n of 246. So that means sample sizes of 246 or larger will deliver a margin of error accurate to plus or minus 0.5 gallons. In other words, the sample average will be accurate to plus or minus 0.5 gallons. Okay. If, on the other hand, I have a proportion, remember like something like the percentage of people who own, say, a smartphone, that would be a proportion, or the percentage of people who use a particular smartphone feature might be more relevant for if you're designing features of smartphones, then one nice thing about that situation is you can design the survey sample size to defend yourself against the worst case. The worst case would be, of course, the situation where the population is most variable, and that would be the situation where the population proportion of people who use that feature in my example is 0.5. So whenever I have a proportion, which is an average of something that's either 0 or 1, you have it or you don't, then you can actually use a worst case scenario where sigma squared is equal to 0.25. And E is my margin of error here. Now remember, a proportion is between 0 and 1. It's a decimal fraction, right? So 0.6 means 60% of the people use the feature. So E is pretty easy to determine as an input. So in other words, here I'm going to be plus or minus 5%, right, or 0.05. I'm going to again use this 95% interval. If I put those numbers in the calculation, here's my E, so it's E squared in the denominator. Here's my Z squared, and here's my variance, sigma squared here. That's the maximum variance. And I get an n of 384. So if I use a sample size of 384 or larger, I will ensure the sample proportions are accurate to plus or minus 0.05 or 5% for any population. So that's actually something that's quite usable. All right, what about, suppose you're using a 5-point scale. It's common to use 5-point and maybe even 7-point scales for things that are ordinal, like the importance of an attribute, your satisfaction with a service, or what have you. And again, you can calculate a worst case scenario. And I would say the worst case scenario you could probably see is something where you have a uniform distribution. So people are using the entire scale from 1 to 5. Typically, that doesn't really happen. Typically, you have people either really satisfied or really unsatisfied or think it's really important or don't. But this is kind of a worst case scenario, in which case the variance would be equal to 2. That's something I calculated for you. And I'm going to use an E margin of 0.25. Again, this is on a 5-point scale. That's a pretty strong, tight margin of error. I'll use the same 1.96 as I did before. And here we see, lo and behold, you get a sample size. Here's my E squared. Here's my Z squared, and here is my maximum variance. Worst case scenario, I get an N of 122. So estimating things on a 5-point scale, you can get away with moderately small samples. Okay, that concludes my little tutorial. I hope that provides you with some insight and reminds you of a few of these basic concepts from data and decisions or your basic stat course, which of course we do use in practice all the time. So happy surveying.